Sometimes in math, we want to know how far apart two numbers are. To do this, we can subtract the two numbers, and the result is the distance between the numbers, for the most part. This concept holds true as long as we do the greater number minus the lesser number, but if we flip the two numbers around, we get a negative result. And since we generally don't think of distances as being negative numbers, we can fix this problem by simply getting rid of the negative sign, so that the number is positive. In fact, this concept of making a number positive comes up often enough in math that we give it its own name, the absolute value. To make the absolute value a bit more formal, let's define the absolute value of a number as the distance of that number from 0. For positive numbers, this is really easy. The distance from 0 is just the number itself. Take 5, for example. If we look at the number line and count out the distance from 0 to 5, we get a distance of 5. For negative numbers, this process is almost as easy. We can look at the number line and count the distance from 0 to our number, and the distance ends up being the same as our number, except that it's positive instead of negative. We can represent these concepts mathematically in the following way. Notice that we drew two vertical lines or bars around the number that we want to take the absolute value of, and that the answer is the absolute value of the number inside the bars. We can extend this idea to create an even more formal definition of the absolute value by making a piecewise function. Notice on the left side of the equal sign here that we have the absolute value of x, which is the expression that we're defining. Then, on the right side of the equal sign, we have this curly brace, which indicates that we have multiple cases to consider. In the first case, when x is greater than 0, the absolute value of x is just x. But in the second case, when x is less than 0, the absolute value of x is equal to negative x, since the negation of a negative number is positive. Now, you may have noticed that we haven't discussed the absolute value of one special number. We've talked about the absolute value of all the positive numbers and all the negative numbers, but are there any numbers that are neither positive nor negative? Well, yes. 0 is the boundary between the positive and negative numbers, so it doesn't fit into either category. So what's the absolute value of 0? Well, it would be the distance from 0 to 0, which is 0. This means that we can adjust our representation from earlier just a bit by adding a greater than or equal to symbol so that 0 is included in our definition as well. And with that, we've defined the absolute value. Now, let's look at some examples. To start, here are some basic absolute value expressions, and here are their corresponding values. Next, here are a couple problems where we need to do some operations before we take the absolute value. For example, in the first problem, we start by doing 2/3 minus 4, which is the same as 2/3 minus 12/3, which is negative 10/3. Then we take the absolute value, which is positive 10/3. In all these problems, the absolute value bars function kind of like a set of parentheses as far as the order of operations is concerned. We evaluate everything inside the absolute value bars before we actually perform the absolute value. Now let's look at a couple problems where some numbers are outside the absolute value bars. In this problem, we start with 6 and then subtract an absolute value expression. And since the absolute value bars act like a set of parentheses, we need to evaluate that portion of the problem first. This gets us the absolute value of negative 8, which is positive 8. And then we do 6 minus 8 to get a final answer of negative 2. Notice that even though there was an absolute value in the problem, our final answer can still be negative. You might be tempted to say that the final answer should be positive 2, but remember that the absolute value only applies to the expression inside the bars. Next, let's look at this problem. It might seem pretty straightforward, but one aspect of the problem that can trip people up is the subtraction inside the absolute value bars. The temptation for some is to turn it into a plus sign since the absolute value makes things positive. Remember, though, that the absolute value bars function like a set of parentheses, so our first step is to evaluate the expression inside the bars, which is 7 minus 2, not 7 plus 2. And since 7 minus 2 is 5, we then take the absolute value of 5 and multiply that by 4 to get our final answer. For this next problem, we have two different absolute values to calculate. We evaluate the expression inside each pair of absolute value bars first, and then we take the absolute value of both quantities. Finally, we multiply the results to get 105. And finally, we have a problem with an absolute value inside another absolute value. Just like we would do with parentheses, we start with the inner set of absolute value bars, which evaluates to 5. Then, we multiply by 2 and subtract that from 8 before taking the absolute value again and adding 5 to get our final answer. Now that we've practiced using the absolute value, let's evaluate some functions that contain the absolute value. For this first function, let's start by calculating f of 7. Remember that this doesn't mean that we're multiplying f times 7. Rather, 7 is the input of the function. So we simply replace the x in the function rule with a 7, and then evaluate the resulting expression to get an answer of 6. Let's also calculate f of 1. Once again, we just rewrite the function rule, except that we replace the input variable with a 1. Then we evaluate the resulting statement to get 4. The same principles apply even when there are multiple x's in the function rule. Take a look at this second function. We want to calculate g of 7.4, and since 7.4 is taking the place of the x, we replace all of the x's with 7.4. Then, we do some calculations to get our final answer. And here's one more example of this process, but with a fraction as our input this time. With that, let's practice evaluating one more function, but this time we're going to represent our inputs and outputs with an extended table of values. And while extended tables can be beneficial for breaking a function down into smaller steps, the challenge here is knowing what those steps will be. Let's start, though, as we've done before, with our variable x. Then we ask ourselves, what's the first thing happening to x? And if we look inside the absolute value bars, we can see that right away we're adding 5. So our next column is going to represent x plus 5. From here, you might look at this function and think that there are just 2 more steps to complete, multiplying by 3 and adding 2. But this ignores one crucial step. These are no ordinary parentheses in the problem. These are absolute value bars. In fact, once we've added 5, our next step is to take the absolute value. So we'll add that to our table. Next, you might see the plus 2 after the absolute value bars and think that our next step is to add 2. But what about that 3 in front of the absolute value bars? Well, since multiplication comes before addition in the order of operations, our next step is to multiply by 3. And then we can finally add 2 to complete the process. Now that we've determined what each column will represent, we're ready to fill in the table. For our inputs, let's choose the integers from -6 to 0. And then, for each of those numbers, we'll need to add 5, take the absolute value, multiply by 3, and add 2. And there you have it, an extended table of values for an absolute value function. In order to develop a deeper understanding of absolute value functions, let's practice converting between function notation and function machines. In fact, let's start with the function that we just made an extended table of values for. Then, in order to make our function machine, we can first write down the name of our function, and then we need to ask ourselves, what sequence of steps is happening to the input of the function? This line of questioning might sound familiar, though, because it's essentially the same question we asked ourselves when making the extended table of values. The sequence of steps that belongs in our function machine corresponds directly with the steps that happened in the column headers of our extended table. So let's put a copy of that extended table on this screen. Once we have that written down, we can see that the first step we took in our table was to add 5. So let's make that the first step in our function machine as well. Next, we took the absolute value. The main question here is, how do we represent the absolute value inside a function machine? Well, we could draw 2 vertical bars, since that's how we typically write the absolute value. But that ends up looking kind of like the number 11. So instead, we're going to write the letters ABS. This is a common abbreviation for the absolute value, and you might have even seen this abbreviation before on a calculator or in computer code. From there, our next 2 steps are to multiply by 3 and to add 2. And once we add those steps into our machine, we've completed our goal of converting our function notation into a function machine. For one more example of this process, consider this function d of x. We can see our first step inside the absolute value bars where we add 12 to x. So let's also put a plus 12 in our function machine. Our next step is to take the absolute value, which we'll once again represent in our machine with the letters ABS. And then we're dividing the absolute value expression by 5, so we'll write division by 5 in our machine as the last step. And finally, let's do an example where we convert from a function machine back into function notation. We could once again use x as our input variable, but let's mix things up a bit and use t instead. So we'll put t into our machine and then check out the first step, which is to multiply by 5.2. This gives us the expression t times 5.2, but we'll write it as 5.2t. Then we need to subtract 1.4, which gives us this expression. Next, we take the absolute value, and all we need to do to represent that is to draw vertical bars around our expression. And for our final step, we're going to multiply by -1. And while there are many ways we could represent this, we're just going to put a negative sign in front of our expression. Once we've done all of this, it's time to write out our actual function notation. Since our function name was a, we're going to start by writing a with a set of parentheses after it. Then we put t inside the parentheses to indicate that t is our input. And lastly, we need to indicate that a of t is equal to the output of the machine, which is this expression. So we copy that expression into our function notation, which successfully completes the conversion process. That concludes this video on evaluating absolute value expressions. Hope you learned something new, and thanks for watching.